hello. What I wanted to do is sort of walk you through a journey. I've been studying this problem for a couple years now, and there's a ton of trade-offs, as Thomas mentioned, and the right technology solution is really a little bit in the eye of the beholder. I'm going to show you Qorvo's perspective and some of the reasoning behind it. So what I'm going to first introduce is talk about the fixed wireless use case. That is really what's driving things today. And then get into some of the base station architectural trades, because there's several ways to do this, and the technology front-end choice really does change. I'm also going to talk first about the two main architectures. One is the all-digital beamforming architecture, and then get into hybrid beamforming architectures and talk about some of the trade-offs and compromises that go along with it. So, what's a little bit exciting is that 5G is actually here. So I highlighted Samsung's base station because I think it's a very cool example of some of the major trials that are ongoing. And in this case, they actually have 1,024 elements and from 4 different panels, and consuming quite a bit of power, in my estimation, of about 200 watts just for the RF components. And that's a key thing you have to consider, is this box, there's no fans in this box. So power consumption is quite critical. Power dissipation and form factor actually is driving some of the semiconductor technology choices and power levels, and that's quite critical. Although cost is king, efficiency actually of the front end comes in right behind that. But 5G is here. Again, I'm going to talk about the fixed wireless access use case. Primarily, of course, 5G is the platform for many technologies, many use cases. But in this case, I'm just going to talk about fixed wireless. Certainly, the frequency bands, we've been talking about these for several years. They're defined by 3GPP. And I threw this technology because not all semiconductor technologies can operate up in these high frequencies. And so I've shown several choices, silicon, SiGe, SOI, and RF CMOS. Gas technologies have been doing that for years and years. And of course, at Qorvo, we have even 90 nanometer GaN technology that can go well over 100 gigahertz. So we've been sort of waiting for the 5G millimeter wave use case to come along, and we're very excited about it. So first thing when you're looking at the applications is use cases. There's a number of very short-range use cases being studied by 3GPP, but the one that interests me is this 500-meter inner sight distance case and understanding what's required to close that link. And a key point to my perspective is that coverage has to come first. We're going to move to millimeter wave, which gives wide bandwidth, but if the capacity is only 30 meters, it's going to be a tough sell out in the market. So a number of studies have been put together that really compute the path loss that's required to close this link. And what I've shown here is the probability that you're actually going to get coverage. So normally you would choose a point down here such that 99% coverage in an area, but if it's fixed wireless access and maybe you can run a truck out there and put something on the roof, perhaps only 20% coverage in a self-install application would be needed, and then the rest may be a professional install for the time being. And to close that link, you need 165 dB of path loss. So that's really where my starting point is. And when I look at the use case for a 500-meter inner sight distance, what you see is there's cell towers getting right in the middle of your neighborhood. And this is a key challenge, is the logistics and deploying those base stations. So even at 500 meters, we've got a problem. And so carriers are trying to get outside the neighborhood. And so that's where this coverage and range is actually quite critical. I did put together some basic parameters that maybe calculated how much revenue they're going to get per square kilometer per year. Of course, you tell me whether this is a good number. It all depends on the costs. And if you have to rent a bunch of towers, that cost will be eaten away quite quickly. But that's the point, is that carriers would really like larger cells, as large as they can get to stay out of that neighborhood. So you can go through a link budget analysis and really convince yourself that I'm going to need an EIRP of 66 or 65 dBm in order to close the link for a 200 megabit CPE that's on this edge of the cell. And so that's kind of what I've computed here under some typical and notional conditions. Now the FCC has allowed much greater power levels, 75 dBm per 100 megahertz. And so really what's limiting us to this 65 or 66 dBm is the technology. They cannot dissipate enough heat from that base station to get higher powers. And so that's really the challenge we're trying to solve here. So a quick summary, and I'll go into the next section. Fixed wireless is here. It's being deployed today. 28 and 39 gigahertz are the lead bands. 26 gigahertz bands will be coming next year. We need 165 dB of path loss, which means a base station of at least 65 dBm. You know, in one of the rare instances, the regulatory is not actually the limiting factor. And of course, the semiconductor technology really depends. So let's get into some of those trades. So we need to build a base station that's 65 dBm. It's got to be low cost, and as I mentioned, allow all passive cooling and tower top electronics. And so big questions are, how big should my array be? How many active TR chains do I need? Something that Tom addressed, do I really need 2D beamforming, or is 1D okay? And some other trade-offs that I'll go through here. And in the end, we're trying to figure out, you know, will I need 3-5 front ends, or with enough elements, can I get away with an all-silicon solution, which has been a major hot question over the last few years. So these are the deployment scenarios, and what I'm trying to point out here is that you don't need a very large scan range in this direction. You need good scanning in this direction, but not in this direction for a suburban fixed wireless access deployment. The case that's often made is that in this urban environment, you need more scan angle. But often you just find the tallest building next door and put it on top, and that way your scan range is limited. Also, the range here is quite limited. So it really might be a different class of base station that you would use in an urban environment. So one of the key trades we've looked at is, do I want to passively combine multiple elements together and drive them with a bigger PA, or drive each element independently? And so the PA that you design is completely different depending on this trade-off. So I would argue that in the suburban case, since you have limited scan angle, you can actually combine antennas together and feed them with a larger PA. Now, of course, we want good beamforming in the horizontal in order to set up different MIMO and multiple streams. And to do that, it's generally considered that, you know, perhaps less than 13 degrees is sufficient to give you some beam separation between users. And so you can start to get a feel for, you know, one phased array design for suburban applications. Now, the next trade-off is, do I want separate transmit arrays and receive arrays? And what that means is that I can actually have more room for my components. And so I've shown here that the PA can be connected directly to the antenna, and the LNA can be connected to this antenna, and those two antennas can be separated apart for better isolation. And so, but as it turns out, in the industry, we're driving towards integrated transmit and receive arrays. And that's really doubling the amount of integration that has to happen here at the front end. And also, we have to deal with the switch losses that are now present in that architecture. To take it further, these systems are dual polarized typically. And so I can create a panel with one polarization and a panel with a separate polarization. But the industry is really driving towards an integrated panel. So now I've really increased the complexity and integration, 4x compared to a separate panel solution. So one of the keys that we're trying to solve is how to pack so much stuff into such a small space. And that's really changing some of the game. As an example, you can barely see this, but this is an array at 39 gigahertz. So you see there's not a lot of room to begin with, and then you're going to pack a number of active channels together here. So quite a space-saving problem. The reason they want integrated TR is because of reciprocity. They want to be able to listen to the uplink and use that information to transmit on the downlink. To do that, they need to be calibrated, and to be calibrated, they need to reuse the same antenna aperture. So a quick summary, I believe that full two-dimensional beamforming isn't really required for a lot of the use cases for fixed wireless. We said we needed at least 8 columns to get that separation in the horizontal domain, and that transmit-receive integration is preferred and dual polarization is preferred, which brings up a very challenging problem in terms of integration. So let me move on to all digital beamforming and talk about that for a minute. It's logical to start at this place because sub-6 gigahertz mass MIMO architectures are already all digital beamforming for many, many good reasons. And if we look at this mass MIMO platform, this is a typical sub-6 gigahertz platform. You would have a 2x2 transceiver, a highly integrated front end using a Doherty PA, and an integrated receive switch LNA module. And so if we want to do this at 28 gigahertz, what we need is new transceivers that put out very high frequencies, similar to what Analog Devices was showing. We're going to need new integrated switch LNA modules that are suitable for millimeter wave, as well as high efficiency PAs at 28 gigahertz and 39 gigahertz, which really hasn't been done in the past. Now, if we start our analysis using off-the-shelf components from today's technology, you can actually formulate a system that achieves our goal of 65 dBm. And what we can do is kind of go around here and add up the power consumption of that typical system. And not just as usual, the PA dominates that power consumption. And if we add up the amount of power we need for this system, we actually end up somewhere near 334 watts, which is very hard to dissipate on the tower without a very big heat sink. And so the conclusion so far is that all digital beamforming at millimeter wave is tough. And we really need to have some new components to be able to enable that. And so what we've created is a high power multi-stage Doherty power amplifier that provides greater than 20% efficiency. So getting from the single digits to 20% is a huge lift in efficiency. And if I just take this one component and replace it in that previous system, I can actually achieve that 200 watt type power number if I change nothing else in my system. So that's really the point of this development for this PA. It's 10 watts, achieving greater than 24% efficiency at 2 watts average output power. And so we're hoping that this is actually a real enabler for the all-digital beamforming solutions at millimeter wave that are yet to come. And here's an example of that performance lift that you get compared to a traditional PA to a Doherty PA. Okay, so it seems logical just to extend my current mass MIMO base station at sub-6 gigahertz to millimeter wave. Unfortunately, today's components are a little bit too expensive in terms of power consumption, but we've created a new front end, and in combination with improvements in A to D and D to A converters as they go to smaller and smaller nodes, I think we'll see a lot more all-digital beamforming architectures at millimeter wave very soon. But right now, hybrid beamforming is really being investigated seriously, and most systems are based on hybrid beamforming, so let me talk about that. So it's kind of important to understand what you're giving up compared to an all-digital beamforming. And so I'll go through some of those things to help you understand what we're giving up. You have to make some key selections in terms of the number of elements and the semiconductor technology. And again, back to this question of, does SiGe solution really scale to high EIRP? So I have some analysis that tries to answer that question and show you some of the trade-offs there. Of course, Qorvo has a number of process technologies, GaAs and GaN, but we're also a big developer in silicon solutions. So we're not necessarily married to only GaAs and GaN, but we want to try to come up with the right answer. So that's what I'm going to show you. So here's an all-digital beamforming architecture where you might do the beamforming, in your FPGA or signal processing. And the neat thing about this is this K is really your subcarrier, so you can do frequency selective beamforming. To do the equivalent in analog beamforming, you end up with what I call the fully connected beamformer, and you can see it's quite a complex unit. In fact, too complex to date. And so what we're seeing initially is a compromised system where we break that fully connected beamformer down into 4 panels. That means you need 4 times as many antenna elements, 4 times as many PAs, etc. And so the question is this a good trade-off? But I wanted you to understand, one of the compromises in hybrid beamforming. The cool thing is I can use each one of these panels to talk to different users, or maybe combine them together to extend my range. And so there is a nice, elegant scalability around this architecture. So to get into it more, as I mentioned, digital beamforming allows me to beamform every subcarrier of my OFDM waveform and service different users within that frequency band, whereas a single phase shifter in RF domain is flat across frequency. And so when you're in a line of sight environment, that can be okay, but when you have wide bandwidths in a frequency selective multipath environment, that becomes a challenge or a compromise. And this just is meant to highlight that. If I have a frequency selective channel and I can't adjust the beamforming weights for this frequency band, then I'm going to have some lost subcarriers and lower capacity. If I can beamform that, I can bring all of these above water and support a higher throughput channel. Or alternatively, I might be able to assign different subcarriers to different users within that time slot, which is really what sub-6 gigahertz all-digital beamforming is doing. The other major compromise that people are trying to solve today is if you look at mass MIMO architectures today, they use digital pre-distortion in conjunction with a Doherty PA. And this is a one-to-one relationship. So in a hybrid, you have a one-to-many relationship. And it's unclear whether digital pre-distortion can be used and how best to use it. So it's an ongoing research project that is quite important, because if I don't have DPD, then I have to use linear PAs, and the efficiency is lower. So getting back to the architecture and some of the semiconductor technologies, as we mentioned, most of the A to Ds and converters and mixed signals all done in CMOS. And then there's kind of a question mark about the beamformer. All these phase shifters and VGAs have a lot of I/O, and it's very convenient to integrate that into a single RFIC, typically in a SiGe SOI type technology. And the real battleground has been, do I need a GaN or GaAs front end? And how best to integrate that? Because I mentioned that integration problem, I got to fit everything into a very small space. So Thomas talked about this, but as I increase the amount of elements in my array, the beamforming gain goes up, and then the PA power goes down. So this is the average power on this axis here. If If I make the array big enough, I can achieve a high EIRP even in a SiGe technology. The question comes in, is that the best way to do it? Is it the most efficient from a power consumption point of view? Because what you see is there are solutions all the way along this track, and those solutions change your technology selection. And so if you want 256 elements, you might be driven into a GaAs or GaN technology. The beamformer unit, and this is just one example, those phase shifters and VGAs are not for free. Those actually consume around 200 milliwatts per channel. And so although at first you get a good benefit from beamforming gain as you increase the element count in your array, at the end there's actually an inversion here where the power consumed in the beamformer unit itself starts to overtake the equation, and you actually find that it goes up. And so what we're really looking for is architectures and solutions for the front end that drive this optimum point. And so you'll see Qorvo's portfolio is really centered around these two types of optimal points. Of course, it's well known that compound semiconductor technologies can improve noise figure compared to an equivalent SiGe technology. And of course, that's going to keep your array size smaller and power consumption lower. So here's one example of the product that we've recently developed. My marketing folks have blurred it out for me. It's got a switch, a PA, three-stage PA, and LNA. And we put two in a package, and that two in the package allows you to fit it very closely on the PCB and solve some of those integration troubles. This one's at 39 gigahertz, but of course we have similar ones at 28 gigahertz and 26 gigahertz that are coming. One of the key questions about GaN technology is it linear enough? And so this shows us achieving a 3% EVM at a power target of around 23 dBm average power. And so just like a GaAs technology, the linearity is quite good. So we're pleased with the EVM performance out of our GaN technology. As I said, we have a family of front-end modules. This is one application. It's that card that I held up, basically. And so you can build a panel of your base station in this way using these integrated front-end components. And it's really a concert between a highly integrated beamformer in SiGe technology and then, of course, the high-power GaN front ends here. And so this example is for a 55 dBm EIRP system. And, of course, power consumption is only 38 watts per polarization. So quite efficient. And this brings me to one of the final points, is that when we compare a SiGe solution, you can achieve high EIRP. In this case, this is what you would need to achieve 65 dBm. But of course, the power consumption is quite high. If you were to compare it to a SiGe plus GaN FEM solution with only 1D beamforming, you can actually bring that system down to something much fewer, only 24 channels. And what I've done is compared the raw die cost of silicon of this solution, which is in SiGe, versus a GaN solution, which has a combination of SiGe and GaN. And what you find out is that there's really 16 times less die area, 10 times less board area. It consumes 40% less power, and is actually 80% less cost, which I think surprises people because they view silicon as being the low-cost technology. But when you're developing a system, you really got to think about it from the system level, not from a per die or per channel level. And so in summary, what we talked about is that fixed wireless access requires high EIRP. There's two main architectures. Hybrid is leading the way, but I believe all digital is going to get there. As the number of elements go up, the PA semiconductor technology changes. And currently all silicon front-end solutions are possible, but not necessarily optimal. If you can plug it in a wall or keep it indoors where you don't have thermal trouble, it's a nice solution. So I think we'll see some applications there. If it's outdoor and you're limited by EIRP, you've got to make some different trade-offs. We showed the performance of a high efficiency Doherty PA. It's actually, the biggest one that I've seen anyway. And then we said integrated SiGe beamformers with compound semiconductors is actually a nice trade-off, but we need to figure out how to fit it all together. And then, of course, the cost and power trades really can flip at a system level. So be careful looking at cost or dissipated power on a per channel basis. Okay. Thank you.